Moving right along, our next task is to see if we can figure the graph for secant. Let's kind of argue through this a bit. Remember that secant is 1 over cosine, and leveraging the work we did with tangent and cotangent, anywhere cosine, this denominator, anywhere cosine is equal to 0, anywhere cosine has an x-intercept, that's where secant has a vertical asymptote, just like tangent. And so, the vertical asymptotes for tangent are the same as the vertical asymptotes for secant, because tangent and secant both have the same denominator. They have cosine for their denominator. So the vertical asymptote for tangent and the vertical asymptote for secant are identical. Wherever cosine crosses the axis, and we've already seen this, that's at the odd multiples of pi over 2. So if this is pi, there's pi over 2, 3 pi over 2, there's 2 pi, there's 5 pi over 2, 3 pi, and so on. Here's negative pi over 2, negative pi, negative 3 pi over 2, 2 pi, and so on. And anywhere cosine crosses the axis, so the vertical asymptotes are at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. All right? Now, the technique for drawing graphs of secant, and it turns out for cosecant, is first sketch in as a dotted line the graph for cosine. So I'm going to dot a line here in blue. So that's a sketch of what the graph for cosine is. All right? At 0, cosine is 1. The question is, what is secant at 0? Well, secant is the reciprocal of the cosine value. So if cosine at 0 is 1, secant of 0 is the reciprocal of 1. But we know what the reciprocal of 1 is. The reciprocal of 1 is 1. Now, at a certain value, the function value of cosine is 1/2. What's the reciprocal of 1/2? Well, it would be 2. And so at that value, wherever cosine is equal to 1/2, that's where secant maps up here to 2. Wherever cosine is 1/3, secant graphs to the reciprocal. That would be 3. Is it clear that as cosine, as the fraction gets smaller and smaller, 1/10, 1/20th, 1/50th, the function value secant is the reciprocal. Those values get higher, 10, 20, 50, and higher. And so it turns out that the graph of secant looks like this, and the same thing happens in this region, where this is 1/2, that's where this is 2. And so the graph of secant, they're not parabolas, they have sort of that look to them, but that's the graph of the secant curve in this region. Now the same thing happens here in this region, except everything is below the axis, everything is negative. And so you generate this, and then the same thing repeats itself, the same thing repeats itself, the same thing repeats itself, and it repeats itself in both directions. And so you get what one student once called this collection of horseshoes. This is the graph of the secant curve. The guideline is, whatever you're going to graph with secant, first do as a dotted line the graph of the associated cosine curve. And then it's rather like this thing just explodes out. Wherever cosine has a node, remember the language? Wherever cosine has a node, that's where secant has a vertical asymptote. And then you have these, they're not parabolas, but again, a student described these as like horseshoes. You have these curves. They're tangent at 1, they're tangent at -1, tangent -1, tangent at 1. All right? So, I'm going to erase some of this so we can get our facts, and that'll be it for our secant function. So, we have domain. Well, the domain is all the axis except we need to throw out the vertical asymptotes. We know what the vertical asymptotes are. They're the same as the vertical asymptotes were for tangent. So the domain is all the real numbers except you throw out odd multiples of pi over 2. Remember the symbol for odd multiples, 2k plus 1. Anyone who knows what you're doing knows this represents odd. This is an odd multiple of pi over 2. Odd multiples pi over 2. There's the domain. Now the range is a little bit dicey because we are using this part of the y-axis, but notice we are not using it. There's no graph in this part of the y-axis. Neither is there a graph in this part of the y-axis. But we are using this part of the y-axis down below. So the range consists of all the values from 1 up to positive infinity, and also the values from -1 down to -infinity. And so we may write that as -infinity to -1, close bracket, because you actually do achieve that point. There actually is a point on the value, on the graph at -1. And then usually we write a union symbol. If you just write a comma or a semicolon or just write the word and, that's fine. This is the union symbol. Technically it's the word or, but you can write the union symbol if you wish. If you wish, you may simply write a comma or just leave it empty. And then the piece up here is from 1 to positive infinity. So there's the domain, rather complicated to write. There's the range, rather complicated to write. All right. The period. The period is the minimum distance over which to repeat itself. Well, it's not too hard to see that the graph of secant depends entirely on the graph of cosine. And since the standard period for cosine is, or the period for cosine is 0 to 2 pi, the period for secant is also 2 pi. That's the minimum distance over which it's required to repeat itself. From here, how far do you need to go to repeat that point? You need to go from 0 to 2 pi. That distance is the period, that's 2 pi. And then the interval, standard interval, is the same as it is for cosine. The standard interval is from 0, well, we're at this way. 0 less than or equal to x less than or equal to 2 pi. So those are the basic facts for the secant curve, and then what we'll do next is we'll come back and just display all of them in much quicker fashion for the cosecant curve.